Hello, quantum strategists. The objectives of this video is to discuss alternative quantum computing technologies and propose a methodology for analyzing, comparing, and ranking them effectively. Understanding quantum computing technologies is absolutely crucial for quantum industry investors, as the technology choices significantly impact companies' valuations. In the complex and challenging world of quantum computing business, comparing companies like Booz Allen Hamilton, D-Wave, and IBM can often lead to confusion due to their vastly different contributions to the field. As a full disclosure, I should mention that I used to be a partner at Booz Allen Hamilton and an executive at IBM. It is essential to recognize that the quantum computing industry includes very distinct segments: hardware, software, and business applications across various industry segments. Each of these areas presents unique challenges, risks, and levels of investments, and most importantly requires different capabilities necessary for success. Hardware and technology development are currently the critical bottleneck. Despite the hype, practical quantum computing applications remain out of reach. In my view, a quantum computer with 1000 fault-tolerant qubits would be required to demonstrate a sustainable quantum advantage over classical computers. However, achieving even 50 to 60 fault-tolerant qubits would mark the beginning of practical applications, a milestone yet to be reached as we struggle to create a single fault-tolerant qubit due to high error rates. The quest for quantum computing has led to exploration of several innovative technologies. Companies like IBM and Rigetti are pioneering superconducting quantum computers. IonQ is advancing with trapped ion technology, and Microsoft is developing topological qubits. Let's start the journey to demystify the quantum computing technologies shaping up the future.
Quantum computing, it's a game changer. Shift in the paradigm, rearranger. It will shape the future like no other. Step up your game, be a quantum brother. Quantum computing, world get ready. Revolution coming, no time for steady. Learn the ropes, go forward fast. Charge ahead and leave competitors in the dust.
There are 7 major types of quantum computing technologies that are competing for dominance. Those technologies are trapped ion, neutral atom, nitrogen vacancy centers in diamond, superconducting, quantum dots, photonic, and topological qubit. We will review and analyze all of these technologies. But before I start the review of quantum technologies, let me offer you a summary that will hopefully pique your interest and motivate you to dive deeper into the quantum computing technologies. Our goal is to provide you with the knowledge to evaluate these evolving technologies and help you to make informed decisions about where to invest in the quantum computing industry. Out of the 7 leading quantum technologies, superconducting qubit and trapped ion are the most prevalent. Industry giants like IBM and Google are using superconducting qubit technology, while IonQ and Quantinuum are developing the trapped ion technology. Our analysis yielded some unexpected findings. It's actually the topological, photonic, and neutral atom technologies that show most promise at present. While still in its nascent stage and largely theoretical, topological quantum computing holds immense potential. Given the lack of concrete experimental results, our assessment is speculative, but the future of topological qubits can be very exciting. Photonic qubit technology is also in its early stages. However, tangible progress has been made with Xanadu's creation of the first quantum computers. Additionally, PsiQuantum has an objective of building a large-scale practical quantum computer with million qubits by the end of this decade. The third technology to watch is neutral atom qubits. Atom Computing recently announced a quantum computer with a record-breaking 1,180 neutral atom qubits. As we proceed, remember that the sheer number of qubits isn't the sole or even the most critical measure of quantum computers' capabilities or future potential. Given insufficient information about the nitrogen vacancy centers in diamond technology, we did not include it in our assessment. And now let's get back to 7 key quantum technologies and outline an approach to assess them effectively. We'll start with an example of quantum computing technology where electrons are used as qubits. So let's start with technology number 1, trapped ion technology.
A trapped ion quantum computer uses individual ions, charged atoms, held in electromagnetic traps to perform quantum computations by precisely manipulating their quantum states as qubits. Ytterbium and barium positively charged ions are frequently used in trapped ion quantum computers.
Now let's discuss how we can assemble multiple ytterbium ions into a quantum computer. Ytterbium ions carry a positive charge, allowing us to use electromagnetic field to firmly hold them in place. These specially designed locations for keeping the ytterbium ions in specific positions are called ion traps. These ion traps are placed inside a vacuum chamber, isolating them from the external environment. The trapped ion computer includes 3 main systems. The first one is ion preparation and placement system. This system is responsible for creating and initializing the ytterbium ions and positioning them in the ion traps within the vacuum chamber. The second system is gate computation system. In this system, multiple lasers are employed, each focused on individual ytterbium ions within the vacuum chamber. These lasers initialize qubits, place them in superposition, entangle them, and perform gate operations both on single qubits as well as on multiple qubits. The third system is computational readout system. It includes lasers and light detectors. By shining a resonant laser on qubits and causing their state to collapse, we can measure their states by detecting the emitted light. This high-level description outlines the fundamental principles of a trapped ion quantum computer technology. Companies like IonQ and Quantinuum are using ion trap technology for developing their quantum computers. And now we are going to review the second quantum computing technology, neutral atom technology.
A neutral atom quantum computer uses individual neutral atoms as qubits for performing quantum computations, often by trapping and manipulating these atoms using lasers. Unlike charged ions, which are used in trapped ion quantum computers, neutral atoms have an equal number of protons and electrons, making them electrically neutral.
In neutral atom quantum computers, the most frequently used qubits are based on rubidium, cesium, and strontium atoms. These qubits rely on nuclear spin to represent states 0 and 1. Operational principles of neutral atom quantum computers share some similarities with the trapped ion technology. The process begins by heating metallic strontium or whatever atom you choose and converting some of it into a vapor phase. The resulting free strontium atoms are then directed into a vacuum chamber where they are trapped and manipulated using precisely focused laser beams known as optical tweezers. Inside the vacuum chamber, these atoms are cooled with lasers down to near absolute zero temperature without needing to refrigerate the supporting hardware. Another set of lasers is used to control qubits and perform quantum gate operations. Lasers together with light detectors are also employed in the readout system to measure the states of qubits once calculations are completed. Atom computing that recently announced the creation of record-breaking 1180 qubit quantum computer is using the neutral atom technology to develop and build its quantum computing systems. And now let's review nitrogen vacancy centers in diamond.
A nitrogen vacancy center in a diamond is a unique defect in the diamond's crystal lattice, formed when a nitrogen atom takes the place of a carbon atom and an adjacent carbon atom is missing, forming a vacancy. One of the nitrogen atom's electrons becomes trapped within that nitrogen vacancy center. This trapped electron's spin state is controlled and manipulated, making it a qubit. The electron's spin in the nitrogen vacancy center is used for performing quantum operations and calculations.
To control these qubits, we use optical, microwave, and radio frequency pulses for initialization and gate operations. Companies like Quantum Brilliance are using nitrogen vacancy center in diamond technology for developing their quantum computers. The next technology is a superconducting qubit.
A superconducting qubit quantum computer is a type of quantum computing system that employs superconducting circuits to create and manipulate qubits to perform quantum computations. These qubits are typically made from superconducting materials, which have the unique property of zero electrical resistance when cooled to very low temperatures.
Unlike the first three quantum computing technologies, superconducting qubit computers utilize macroscopic, human-engineered quantum mechanical systems designed to function as qubits, rather than using naturally existing quantum particles. These qubits consist of two small superconducting materials separated by an insulator, forming what is known as Josephson junction. This junction is connected to a capacitor and an energy source. In superconducting materials, electrons travel as Cooper pairs. Due to quantum tunneling effects, electrons can pass through the insulator, resulting in multiple energy states for the entire system. These energy states encode qubit states 0 and 1. The difference between these states is typically characterized by the presence or absence of one Cooper pair on a specific part of the system called the island. To maintain the superconducting state, quantum computers are operated at extremely low temperatures, often near absolute zero. Cryogenic refrigeration systems are employed to cool down the quantum processor as well as some supporting hardware. Microwave pulses are used to control superconducting qubits and to measure their states. Companies like IBM, Google, and Rigetti are using superconducting quantum computing technology to design their quantum computers. We will now review the quantum dot technology.
Quantum dot technology is employed in quantum computing systems where qubits are realized using nanoscale semiconductor structures known as quantum dots. These quantum dots can be fabricated from various semiconductor materials, including silicon, gallium arsenide, and indium arsenide, and are capable of trapping individual electrons. The electron spin or energy states can be used to encode the qubit states necessary to perform quantum computations and execute quantum algorithms. This technology holds promise for compatibility with existing semiconductor manufacturing processes, facilitating integration into classical computing systems.
I just wanted to emphasize two key points. The first one is that in quantum dot technology, similar to superconducting quantum technology, the qubit is a human-engineered object. This will be important when we discuss the quality of individual qubits across different technologies. And the second point I'd like to make is that quantum dot technology is in a great position to leverage the highly developed and very efficient semiconductor fabrication technology. A number of companies like Intel, Quantum Motion, Dirac, and Silicon Quantum Computing use quantum dot technology in building their quantum computers. We are moving now to photonic quantum computers.
A photonic quantum computer uses the unique properties of photons as qubits. These quantum computers are categorized based on the specific physical properties of photons they utilize for quantum computation. Photon polarization-based quantum computers encode quantum information in polarization states, while photon path or spatial mode-based quantum computers use photon paths for quantum information processing. Another type is continuous variable quantum computing, where quantum information is encoded in continuous variable states of light, such as amplitude and phase. Photonic quantum computers have the potential for fast information transfer and processing at the speed of light.
Photonic quantum computers utilize existing fiber optics and semiconductor fabrication technologies to develop photonic quantum processors. The key elements of photonic quantum computer typically include source of photons. That system is used to generate single photons as qubits. Qubit initiation. That system manipulates photons' paths and states by using linear optical elements like beam splitters, mirrors, and phase shifters. Quantum gate execution. This system also uses linear optical elements to perform quantum computations, including entanglement generation. Photon detectors. Detecting the state of photons post-computation for measurement and readout is the purpose of that system. Quantum error correction. This system is necessary to correct errors in quantum states, and it is crucial for reliable computation. Companies like PsiQuantum, Xanadu, Quix, Quandela, Orca Computing, and several others are using this technology to develop quantum computers. PsiQuantum is working toward the ambitious goal of constructing quantum computer with 1 million qubits, aiming to achieve this milestone by the end of the decade. And the last and most fascinating technology is topological qubit.
Topological quantum computers rely on the principles of topological quantum states to perform quantum computations. Instead of using quantum properties of individual particles, topological quantum computers use anyones, which are exotic quasi-particles. These anyones are manipulated in a way that their quantum states are inherently protected from errors and environmental interference, making topological quantum computers potentially highly fault-tolerant and resilient to decoherence.
In the 6 quantum computing technologies we have reviewed so far, the information was encoded in the quantum properties of the particles. Any, even small interaction with the environment can destroy the qubit state along with the information that is stored there. This is the reason why we need to cool qubits down to near zero temperature and place them in high vacuum chambers to maintain their stability and to avoid, to the extent possible, any interactions with the environment. Topological qubits, in contrast, offer much better stability, which simplifies and improves error correction. Information in topological qubits is encoded not in the quasi-particle itself, but in the order in which we swap positions of this particle. On June 21, 2023, Microsoft announced its capability to create and manipulate Majorana quasi-particles. It is important to note that there have been previous claims about the creation of Majorana fermions in 2012, 18, and 2020, but the scientific community disputed all these claims. Detailed understanding of how topological qubits work requires in-depth knowledge of advanced quantum mechanics and complex linear algebra. Presently, Microsoft is the only major player focused on topological quantum technology. Let's define a framework for evaluating these technologies and develop a perspective on the technologies that have the greatest future potential. In 1996, IBM scientist David DiVincenzo outlined 5 key criteria for quantum computers to be practically useful. First, he required the qubits to be well-defined and isolated from the environment, which is a necessary condition for a scalable quantum computer. The second criterion deals with our ability to initialize the state of the qubits to a known state. The third criterion states that quantum decoherence must be long enough to allow sufficient time for gate operation. The fourth criterion is the requirement for the quantum computer to have a universal set of gates, which is necessary to perform any quantum computing calculations. And the last, fifth criterion is about our ability to measure states for the specific qubits without disturbing the state of other qubits. Based on DiVincenzo's criteria, we have selected specific performance metrics, and we will use them for evaluation of quantum computing technologies. First, decoherence time, which is the time that the system retains its quantum properties. Second is the gate error rate for both single qubit and double qubit operations. The third is connectivity, which is how easily and efficiently qubits can interact with each other. Fourth is scalability, which is the ability to increase number of qubits in a quantum computer. And the fifth is the speed of gate and circuit layer operations. So let's create a table with rows corresponding to individual metrics and columns associated with different quantum computing technologies. Based on our understanding of quantum computing technologies and also from the internet, we can fill out the table with qualitative and relative information. Now let's assign quantitative scores for each technology. The first metric is the decoherence time. The highest score should be assigned to photonic and topological technologies. We know that photons can hold their quantum state for a very long time. Topological qubits, where the information is encoded in the topological properties, should also have quite high decoherence time. However, their properties have not been yet demonstrated experimentally. Trapped ion and neutral atom technologies have the decoherence time that is measured in seconds, even minutes, which is also quite high. On the other hand, the superconducting and quantum dot technologies have decoherence time that is measured in microseconds, the lowest results out of all quantum technologies. One of the primary strengths of topological quantum computing technology lies in its stability and low error rates. It is anticipated that topological qubits will exhibit error rates that are several orders of magnitude lower than the error rates for other quantum computing technologies. Based on published results, the trapped ion technology has the next best error rates, followed by the superconducting technology. Trapped ion and neutral atom qubits have very high conductivity. In fact, in these systems, any pair of qubits can be entangled with each other. Superconducting and quantum dot technologies exhibit moderate conductivity. The physical layout of the qubits on the chip often limits the direct connectivity to the nearest or next nearest neighbor. Photonic systems are characterized by low conductivity. The fundamental reason for this is inherently weak direct interactions between individual photons, which makes it challenging to create entangling gates. For topological qubits, high conductivity is predicted. In theory, we should expect robust and flexible interactions between topological qubits. Scalability is a strong point for quantum dot qubits, primarily due to their compatibility with existing semiconductor manufacturing processes. Similar to quantum dot, superconducting and photonic quantum technologies also demonstrate strong scalability potential. Topological qubits too are predicted to be highly scalable. Neutral atom and trapped ion technologies share some similarities. However, they have very different scalability metrics. Trapped ion qubits, being charged particles, naturally repel each other, posing a challenge for creating large-scale quantum computers. On the other hand, neutral atom qubits carry no charge, and they can be assembled in large three-dimensional arrays, offering a distinct scalability advantage. The superconducting and photonic qubits are the fastest in terms of the gate's operation speed. This is due to the high-speed nature of optical and superconducting processes. Trapped ion systems exhibit lower speed when compared to superconducting qubits or photonic technologies. According to some reports, the neutral atom and quantum dot technologies potentially offer a modest improvements in speed over trapped ion qubits. The topological qubits are expected to demonstrate low to moderate speed of operation. The next question is whether the metrics are all equal in their weight. I would argue that decoherence time, gate error rate, and scalability are the most important metrics. Insufficient progress along any of these three metrics is a deal breaker for creating a fault-tolerant quantum computer. Connectivity and speed also are important, but in my view, not to the same extent as the first three metrics. And now we can calculate the weighted score for each quantum computing technology. Voila! Our methodology is not precise enough to differentiate between the scores for topological, photonic, and neutral atom technologies. In my view, they form the leading group, the technologies with the greatest success potential based on currently available information. The second group includes the trapped ion and superconducting qubit technologies, which are currently the most prevalent in the industry. One may argue that the quantum dot technology also belongs to this group. And now let's take another look at the companies that pursue these quantum computing technologies. If you want to bet on one of the technologies that we have reviewed in this video, investing in the companies that develop the technology is the best way to do it. Keep in mind that many of these companies are private. Also, it is necessary to note that for many large players like Microsoft, IBM, Google, and Intel, quantum computing technologies are a relatively small part of their overall business. With that, let's summarize what we have learned today. Key takeaways from today's discussion. Industry competition dynamics. The competition in the quantum computing industry is happening not so much between individual firms, but more between the alternative quantum computing technologies. Dominant technologies today, trapped ion and superconducting qubit, are the most prevalent quantum computing technologies at this time. Technologies with promising future. After analyzing the available data, we believe that topological, photonic, and neutral atom quantum computing technologies are the most promising technologies for the future. State of topological technology. Topological quantum computing technology is still in its nascent stage and largely theoretical, however, it holds immense potential. Developers of the leading quantum computing technologies. Companies like Microsoft, PsiQuantum, Xanadu, Quix Quantum, Quantum Source, Orca Computing, Quandela, Atom Computing, Pascal, Inflection, and Quera Computing are working on what we believe to be the most promising quantum computing technologies of the future. The quantum computing field is evolving rapidly, and many breakthroughs are being developed as we speak. I suggest to update this analysis on a regular basis to keep track of the quantum computing technologies and their development. Dear friends, I hope you enjoyed today's video, and we look forward to see you in our next videos. Goodbye.